Hello, and welcome to the next chapter, section 3.1. In this section, we're going to be learning rules of finding derivatives or shortcut rules so that we don't have to go through the limit of the difference quotient every time we want to find the derivative. So we're going to start with power functions. And if you remember, power functions are of the form like g of x here, ax to the n, where a and n are any real numbers. And a certain type of power function is a polynomial function. So polynomial functions, the sum of these power functions, but restricted to positive integer powers on x. So you should be real familiar with polynomial functions. Power functions aren't quite as covered as much. So before we look at power and polynomial functions, we'll start with the constant function, because that actually sort of is a special case of a polynomial or power function. So the constant function f of x equals c is just a horizontal line. So we know that the slope of that is 0. So we know that the derivative of that is 0. So that's our first quick shortcut rule. The derivative of a constant function c is just 0. And notice that in this section we're using that operator for the differentiation operator here. So you can write f of x equals c as f of x equals cx to the 0, because x to the 0 power is 1. And later we'll see why that kind of matters. The next function is the identity function, so that's just f of x equals x. You know that's a line through the origin with a slope of 1. So we know that the derivative of the identity function is 1. So also another thing to notice is multiples of the identity function, like 2x, 3x, etc. You know, this has a slope of 2. That's a linear function with a slope of 2 through the origin. So that's derivative is 2. This is a linear function with a slope of 3, etc. So any linear function has as its derivative its slope. So now let's look at the general power function where n's a positive integer, or that power is just a positive integer. So these are the things that make up polynomial functions. So let's differentiate x to the n. That's the most basic one. So we have the limit of the difference quotient. And let's look what happens when we expand that binomial x plus h to the n. So this is, you know, if this were x plus h squared or x plus h cubed, you're going to have a longer and longer string of terms. And if you recall, that's using the binomial theorem. You don't worry if you don't remember the binomial theorem. Just know that the only one we're going to need to worry about is this one. We'll talk about that. So notice that when we expand that numerator, those x to the n terms cancel. And then we're going to cancel common factors of h from the numerator and denominator. And only this term is going to be left. So that h will be gone. That will be canceled with the denominator. All these other, once we take the limit as h goes to 0, all these other terms are going to go to 0 as well. So all we're going to be left with is this second term that shows up in the numerator. So all these other terms go to 0, so we can say that the derivative of x to the n is this constant c sub n minus 1 times x to the n minus 1. That's the term that was left when I took the limit. So the only coefficient we care about is that c sub n minus 1. And if you remember the binomial theorem, and even if you don't, it's really not that significant. That c sub n minus 1 is just n itself. So bottom line, it boils down to the derivative of x to the n is n times x to the n minus 1 power. So you can remember it in your head as you bring down the exponent and then subtract 1 from it. Here's the example of binomial expansion, and again, everybody else you don't care about except this one. So gratefully, you can put the binomial theorem aside and not have to think about it again. So let's just look at a couple of examples. So f of x equals x to the 9th. My n is 9. I bring down my 9 and then subtract 1 from the exponent. The derivative is 9x to the 8th. Same thing here. Now let's look at another example or another power function, but this time let's let that power be negative as well. So a negative integer. So let's say d dx of x to the minus 3rd power. Well, again, deriving it from the limit definition, we have our difference quotient. Here we have found a common denominator. I multiplied that h by the denominator. We expand it. Notice that the x cubes canceled, and all that we're left with, once we take that limit as h goes to 0 here, all we're going to be left with is just minus 3x squared in the numerator. So once we take that limit as h goes to 0 in the numerator and denominator, I'm left with minus 3 over x to the 4th once I cancel factors of x. So if we rewrite this with a negative exponent, that's minus 3x to the minus 4th. So actually the same process applies. Bring down the exponent and subtract 1 from it. So actually this applies with any power, not just integers. So any real number in the exponent we can use this shortcut rule on. For instance, s of p equals the square root of p. So when you see radicals, you're going to want to rewrite those as fractional exponents. So this is p to the 1/2. And now we can apply that power rule. So bring down the 1/2, subtract 1 from the power, and I get 1/2 p to the minus 1/2. And that's how we write it, getting rid of the negative exponent. So we also have a sum, difference, and constant multiple rule with derivatives like we did with limits, and that's actually why. That's where they come from. So the derivative of the sum is the sum of the derivatives, if each of these derivatives exist. Likewise with the difference. The constant multiple rule tells you that you can factor out the constant and just take the derivative of the function. But now that's where it stops as far as getting our laws from the limit laws. The product and quotient law does not apply here from limits. Don't try to do that. A lot of people try to do that. That's a common mistake. The derivative of the product is not the product of the derivatives. So we can use all these rules about the power functions and the sum, difference, and constant multiples to find derivatives of complete polynomials, because polynomials are just sums of power functions with integer exponents. So for example, I differentiate this function, and I can differentiate term by term because of the sum and difference rule. So the derivative of 2t cubed is, first I can factor out that 2 by using the constant multiple rule. And then I can take the derivative of just t cubed. Again, I bring down the 3, subtract 1 from the power. And I wind up with 6t squared. Same thing with the next term. I factor out that constant. I take the derivative of just the power t to the second power. I bring down the 2, subtract 1 from the exponent of 6t. And then with 4t, I just have the derivative of 4 times the derivative of t, which is just 4 times 1, or 4. And then I can subtract them as they were in the original function. So I could have a function like this where it's a mixture of positive and negative powers. And the same thing applies. Differentiate term by term. So another example that you'll see in the homework is like find the points on the graph where the tangent line's horizontal. So you translate that to, oh, where's the tangent line horizontal? That's where the derivative is 0. So you take the derivative of this given function, which we found in the last slide, and you set it equal to 0. And then just going back to algebra, using the quadratic formula, these are the zeros of that function. And so you can see the derivative is this parabola, and where the zeros are. And those correspond to the x values for this local max and local min on the original function. Now let's look at the exponential function. So remember, the basic exponential function is just b to the x, where b is some number that is greater than 0. So if we apply, we're going to apply the difference quotient to that, but before we do, I want to point something out. So if f of x is b to the x, let's first find f prime of 0, and the only reason I'm doing this is because it's going to be one of those things that we need to use later. So when I apply the difference quotient at x equals 0, I get this limit. The limit as h goes to 0 of b to the h minus 1 over h. So we're just going to put that aside right now. And now let's look at the general derivative. So again, I have the difference quotient. I can't really do much with this, except I can factor out that common factor of b to the x. But now notice that this limit is in terms of h. This b to the x isn't really coming into play here with this limit. H is what's changing. So I can actually kind of treat that b to the x as if it were a constant, and I can factor it out from the limit. So I have b to the x times this limit. And this was the guy that we looked at up here. So this is, the derivative is b to the x times the derivative of this function at 0. So this is kind of putting it all together. I know that the derivative of the exponential function is just the exponential function times some constant value. Remember, f prime of 0 is an actual number. I'm plugging in 0 to the derivative. So this is telling you that the derivative of the exponential function is a constant multiple of the exponential function itself. So, okay, that's nice, but what's f prime of 0? Well, that of course depends on what b is. So let's go back and look at when b is that constant e. So remember in the last section we looked at the graph of f of x equals e to the x, and we saw that, or we kind of guessed or surmised that the graph, and then of course we verified it with Desmos, the graph of the function of the derivative of e to the x looked just like the original function e to the x. So going back to what we just saw, that the derivative of the exponential function is just a constant multiple of the exponential function. That means that the derivative of e to the x is just e to the x times f prime of 0, which is just this derivative evaluated at 0. So you're not expected to know this, but f prime of 0, or the derivative of e to the x when evaluated at 0, is just 1. So this all boils down to showing that the derivative of e to the x is just e to the x. So the y values on the derivative curve, on the e to the x curve, are actually the same thing as the slopes of the tangents to the curve at that point. So I want you to notice that f prime of 0 is 1 only when the base is e. We'll see later on in the course that this constant depends on what the base b is. So that may have, the last couple slides may have been unnerving. So the good news is that actually doing the problems, it's just a lot easier. So let's look at some examples. So f of x equals e to the 5th. Okay, that's just a constant because e is a constant. So the derivative is 0. G of t equals 4e to the t. I'm going to use the constant multiple rule, right? And that's just as this is 4 times the derivative of e to the t. But the derivative of e to the t is just e to the t. So this derivative is equal to the original function, 4e to the t. And now let's look at another one, f of x equals e to the x plus 1. Well, does that rule apply if the power is not just x? We don't know. But what we do know is that we can use algebra to turn e to the x plus 1 into e to the x times e. So we're using our laws of exponents from way back. And remember, e is just a constant. So this is just a constant multiple of the function e to the x. So remembering that the derivative of e to the x is just e to the x, the derivative of the constant times the function is just the constant times the derivative of the function. And it boils down to this is just e times e to the x, or e to the x plus 1. So we're seeing again and again where the derivative is equal to the original function. So now let's combine a few more things. So in this example, e to the 2.4 power is just a constant, so its derivative is 0. And this is a power function, so I bring down the power, subtract 1 from the exponent. For the second example, I first need to expand this binomial, and then I differentiate term by term and use the constant multiple and the power law. And of course the derivative of 1 is just 0. So I bring down my term, my power, and subtract 1 from it in each case. And then this third one, you see a radical sign, so you want to turn that into a fractional exponent. So I've just separated these by the common denominator, and I simplified. So now I'm going to take the derivative of this. So again, I just use that power rule, and the fact that the derivative of e to the v is e to the v. And there's my derivative. So Another problem that you might see is you might be given a graph and asked, find where the function is differentiable, or is it differentiable at a certain point. So of course we have the proverbial piecewise function. So we want to look and see the limit from the right and the left. So before we would have done the limit definition, but now we can look at each piece. So the derivative for x greater than 1 is the derivative of x plus 1, which is just 1 by the power law. The derivative when x is less than 1, we need to take the derivative of x squared plus 1. So again, we apply the power law, and that is 2x. So since the limit from the right is 2x, and when I evaluate that at 1, I get 2, and that's not equal to the limit from the left, which was 1. So this function is not differentiable at 1. And this dashed graph is the graph of the derivative. So in summary, we now have a quick way to find derivatives of polynomial functions, functions involving e to the x, sums and differences in constant multiples, and piecewise functions. We still need to look at both pieces, but don't forget that the product law from limits doesn't apply. It was just the sum, difference, and constant multiple laws.